So it should say sub goals, right?
Yep.
And I say sub goals because we're trying to understand how the brain not only understands behaviors of objects, but affects behaviors and makes changes in the world and solves goals. And so really what we're talking about is a subset of that, which is, how do we learn models of behaviors? We make an assumption that we learn behaviors, and Vivian had given us some nice pictures of that last week. And then we want to say, how do we predict? One of the things we've been focusing on is how do we predict the changing morphology of objects based on a behavioral model? Like, how can we predict what the stapler will look like when it's opening, or a novel object? And so we want to apply behaviors to not to just the objects that was learned, but to novel objects as well. So this is the only thing I'm talking about today. This is a subset of a lot of stuff we have to do. And we can think about it like, I'm going to just make some statements, make some arguments, and then give you a bunch of examples that I walked through to help me think about this problem. So let me just start with where we ended up. Let me start with a definition. A definition of a behavior is when a child object changes relative to a parent object. We're going to, again, we talked about this before, we're going to abandon the idea that this can be done in a single column. It requires two columns. It requires a parent and child relationship, much like we have with compositional objects. Therefore, behaviors require a parent object and a child object. Okay, so two learning modules. And then I'm going to just state, and we've stated this last week as well, that behavior models exist in the parent object and not the child. So if I have two learning modules and there's a parent-child, a parent object, a child object, behavior model exists in the parent object. We can't do this in a single learning module. So that's yes.
Just to clarify, at the lowest level, like the first definition, where a child object changes relative to a parent object, can this child object be like the feature that comes from the sensor directly that changes, like color changes?
That's a good question. And I've avoided that for now. One of the things I've learned about thinking about hierarchy is that if you focus on the primary sensory regions, it really messes up your brain a bit. And that typically when you figure out the hierarchical relation between two learning modules or two columns, then you can back off and say, oh, right, so what's the exceptions that's happening in the primary one? I didn't do that in this case. It's a good question. I didn't focus on that.
Yeah,
I think there probably will be one thing you might be able to predict changes of orientation, but you won't be able to predict necessarily. You certainly wouldn't be able to predict entire child object changing. So my guess is that it would apply, but with some.
But yeah, it's just simpler behaviors that can be learned.
Yeah, or simpler child objects. Are you willing to accept that, Vivian, or you want to make some more points?
Yeah, no, that makes sense.
So again, this is a subset. So this is a subset of the subset. I didn't deal with that particular point right now. And then this is the main idea that I came up with and Vivian came up with. I think this is what I came up with. I think it's half of what you came up with. That felt like the big insight. And the big insight, and I'll explain this in multiple ways, that what the behavior model, how it communicates with the child. So you have the learning module I'll show images of this in a second. You have the learning module that has the parent object and the behavior model. What it sends to the child object is different than what we've talked about in the past. In this case, it's sending movement information to the child object. In some sense, it's not, and I'll explain what I mean by that. So here's two pictures. On the left is our standard compositional model, and I didn't show all the details here. I'm just saying, okay, there's this two objects, a parent object and a child object, and they have the child object is part of the parent object. It's a subset of it in some sense. We have two morphology models, one for the child and one for the parent. Going back to the coffee cup, that would be the logo on the left and the cup on the right. And the way, and they both are updated. They both have a point where the sensor is focused at that moment in time. So there's some location on the parent object and an equivalent location on the child object. That location gets updated by the sensor movement. So sensor movement comes in, and through path integration, we can move the sensor around on both of those objects. And the objects are tied together by the blue arrow. They're tied together in a way that the location and the ID on the parent object at that location is associated with the location ID on the child object at that location. So we can say, oh, at this point on the coffee cup, we're at this point on the logo. Of course, there's orientation and scale, things like that. But the basic idea, we're pairing on a one-to-one basis, the child object and the parent object. These are tied together through this blue arrow connections. And that relationship changes as we move around in space. So, you know, at a different point on the parent, I have a different child object, and so on. So that's our old compositional model. On the right, I show the same model, but now we've added a behavioral model. The behavioral model is shown in green on the parent. And Vivian, we've talked about what that looks like. I'm not going to show what it looks like here. Just say it's a model of behavior. And in this case, the behavioral model also sends a movement command to the child. We can't tie the behavior, you'll see why in a moment. You can't tie the behavioral model directly to a child object because we want to be able the behavioral model to apply to different children, different environments. So we can't tie the behavioral model in the parent to the morphology model in the child because the behavioral model is going to apply to different children. So the only way you can do this is by sending a movement command to the child. That movement command does not cause the child object to move. It just changes the location of the expected location on the sensor, of the sensor to the child object. It's doing the equivalent of the brown arrow in some sense. It's telling the child object, you know what? It's as if the sensor is moving, but it's actually not moving. We know that the child is moving. This whole child object is moving, but the relationship between the sensor and the child will change. And therefore, if we want to make a prediction, the behavioral model says, well, I know that the child should be moving right now. And if the child's moving, the location of the sensor on the child will be changing. So I'm just going to tell the child object that the location of the sensor is changing, and it can make the correct prediction. It's you know, this is all these what we might call allocentric models. They don't really know where they are in the world. The left learning model doesn't really know where the child object is. It's just saying I have a relationship between the sensor and the object, and I'm going to change that position. So this is the idea about the basic idea about how a behavioral model could lead to predictions in a child as a child object is moving. It says, oh, I know how the stapler top is moving, therefore I can tell well, we'll get into the stapler top in a moment, but I can tell the model that's modeling the stapler top that it's moving through the world, but basically what's going to happen is that where the sensor is going to change. So there's these two sources of movement information. One is the actual sensor is moving relative to the parent. And one is the child is moving relative to the parent, which will make it look like the sensor is moving relative to the child. And that's the gist of the solutions that Vivi and I came up with. And before I go, I'm going to now give you, the next slide will be a whole bunch of examples to walk through just the way to think about this problem. But before I do that, and that'll make this diagram more obvious, but before I do that, does anyone want to ask questions about this? Did anyone not understand it? Raise your hand. Don't be embarrassed. I didn't understand it.
I'm a little unclear, but I'm just going to screenshot this slide and then refer to it while you're going through
It
examples.
might help me, Scott. Tell me what part that's unclear. Everything? Part of it?
Well, like I'm looking at here, it says, let's see, does not cause child object to move. It changes the expected location of the sensor to the child object.
Right.
So I thought that it was the actual child object itself that was moving relative to the parent object.
It is. The child object is moving. But at the moment, the diagram I'm showing is only trying to predict the result of that movement. It's not making the movement happen.
It basically moves you through the reference frame of the child object. So like the reference frame, the more we are in the bottom, the left column, the child column, we have a hypothesized location of where the sensor is in that child object's reference frame. And then that movement command from the behavior model moves that hypothesized location in the reference frame of the child object.
Okay.
Here's
makes sense.
another thing about it. Scott, I understand it's a confusing concept, so I totally get what the confusion is. Imagine, you'll see in a second, imagine I have an object that just has its own behavior, and it's an inherent behavior. No one causes it to do anything. It just does it on its own, right? I'm not making it happen. It just does it. It's like, you know, I'll give you some examples in the next slide, but, you know, the hand on the clock just moves. Okay, it just moves. I don't have to do it. It's just going to do it on its own. So I don't. The cortex or the learning module isn't making that child object move. It's moving, but we have a model of it, and we want to predict what it's going to look like after it's moved or while it's moving. So the goal of this green arrow is not to make the thing move. It's just saying, well, given I have a model of how it moves, what should it look like after it moves? Remember, Vivian or Niels, we had a couple of images where we talked about emotion through an obscured area. I know Vivian had this. And it's like we could predict, you know, if the stapler is opening and it's moving through an obscured part of the scene, we still predict it's going to come out the other side at the right point in time. So we're just trying to make that prediction. We're not trying to make the object move. We're just trying to predict, oh, I know what's going on. I recognize this behavior. Or someone's swinging a bat at a ball. I expect the ball to move. I mean, I'm not making that happen, but I can predict what's going to happen given a behavioral model. And so that's all this is doing. And in reality, changing the location of the sensor to the object is what would happen if the object moved. It's also what would happen if the sensor moved. So you can move one or the other. I could say, oh, my eyes fix it at some point, and I move the object. Well, if I don't move my fixation point, the location on what I see is going to change based on how the object moved. And that's all the green arrow is doing. It's saying the object is moving. What should I predict? And I have to know how the object is changing, how the child object is moving. Its direction, its speed, its change in orientation, all these things that the green arrow represents. I just have to be able to say, okay, well, the child object is moving. Therefore, the relationship between the sensor and the child object will change. I want to make a prediction. I have to predict where that new location of the sensor will be, given the object is moving. I don't know if that helped or not. It's hopefully.
Yeah, that makes sense. It was just like the coupling between what the child object is and the sensor resting on it. It was like a little bit unintuitive at first, but it makes sense now. Like the only thing you have about an object is what your sensor is telling you about it. So
right. So Matt, if you can see my hand here, I don't know if you can see my hand in my image. You know, my finger I'm touching my hand with my fingertips. So this is a sensor and this is the object. Well, our normal models, we move the sensor over the object and we make predictions. Now we're basically saying, because of behavior, the object is moving. And it's the same thing. You know, from the model of this object, it doesn't know, this child model doesn't know if it's moving or if the sensor's moving. It really doesn't know. It just says, okay, there's a sensor at some location. It should predict this. Oh, now it's in a new location. Well, did it move this? Did this move or did this move? It doesn't matter. It can't tell the difference.
And in the case where the sensor is following the object, the kind of smooth pursuit case where we have the sensor is moving and the object is moving, it would basically be that the sensor movement and the movement from the behavior model cancel each other out. So we keep predicting the same location on the child object, which is exactly what we want. If we're following the child, we keep being on the same location on the child object.
Right. So the green arrow and the orange arrow will sort of cancel each other.
Yeah, exactly.
Yeah. I'm not proposing any mechanisms here how to do this. I'm not showing this in layers of cells. I just felt we had to take a step back and try to get the basic idea down. Does anyone else want to ask a question before I go on to the next slide?
Yeah, I have a quick question. So this makes sense to me. And we're talking about movement right now. Are you going to cover cases where like the color is changing? Because that's confusing for me right now.
Yeah, I will, but not as much. I
Okay.
think that's the easier case. You know what? I did think about it, but I didn't put it in my next slide. Well, I have one. I didn't really prepare to talk about that today. This is like the traffic light, you know, it's changing from red to green,
Yeah,
or something
exactly.
like that. I think that's the easier problem, actually. And I didn't develop it here. Today's presentation, all I developed was prediction from movement. So let's come back to it. Can we come back to that at the end? That'd be a good idea.
Yeah, absolutely.
Yeah.
Then
Again, yeah.
just for completeness, I guess, so relative changes in orientation, like if the child rotates relative to the parent, that, like, just to confirm in your proposal, like that wouldn't move you through the location space, but instead it would adjust
Right.
the rotation hypothesis.
Right. I didn't put that in
Okay.
this diagram. You know, like I said, I said the location ID is shared between the parent and the child. Well, of course, we're actually sharing orientation as well and scale, and I didn't put those in there. So this is a real sort of conceptual thing. It's not going to all the things that have to happen. I'll show some of those in the next slide.
Yeah, I think it was a good idea to kind of simplify it because
Yeah,
I mean
exactly.
it already it felt kind of promising and right when you were presenting it last week, Vivian. But yeah, I think it does help to kind of show the kind of core thing, and it definitely seems, yeah, like this could be right.
Right. It's really just this really basic idea that we have two ways for a parent object to talk to a child object. One is through this mechanism we've identified before, which associates the exact parent with the exact child very precisely. And then we have another way which says it'll take the behavioral model and we can't associate that with an exact child. And we can't know everything about the locations and so on. So we have to go it indirectly. So right, if everyone walks out of today, if that's all you remember, that would be successful, I think. Let me show you some pictures here. I apologize. I went back to using the coffee cup and the Memento logo because it was just convenient. I didn't have a Thousand Brains Project logo with me at the moment I was doing this. So apologize for that. There's just 4 little examples here. And what I'm showing, imagine, and so this is a magic cup. Don't ask how this happens, but you can imagine it would happen. So this is what I use in my mental imagery, and so that's what I made pictures of. It's not like, maybe it's not the best example, but it worked for me. So on the left, you can see what I'm proposing here is imagine a behavior where the logo on the cup changed position. And I was thinking like, oh, every 3 seconds it would move from a lower position to an upper position. And then 3 seconds later, it would move back down to the lower position. I'm not showing that movement here. I'm just showing the 2 endpoints of the movement. So you can imagine this logo going up and down. See, I have a Thousand Brains project here. I'm like going, I got a special Thousand Brains project mug. It shows the bent logo. It goes up and down and up and down, and that's the behavior. Well, we can obviously learn that behavior, so we have to be able to make predictions about where the logo will be at every 3 seconds as it moves and the velocity and so on. The second one is we can just change the orientation of the logo. So the logo just rotates, you know, again, same idea. It's changing down and then it rotates up and then it rotates down and rotates up magically. We can also change the scale of the logo where, you know, it goes from a small logo to a large logo to a small logo. And then finally, you can alternate between different object IDs. So we went from the Memento logo to a British flag. And then you go back to the Memento. So magically, it just changes, blink, 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 back and forth. It gets more complicated. You really just can't change the orientation. And so I imagine that when I change the second image here of below the first one, the Memento logo is changing its orientation, but it's it's rotating on a different point. In this case, it's rotating on the corner of the triangle. In the upper one, it was rotating on the center of the word memento, or like around the M. So you can't just say, oh, I'm rotating the logo. That's insufficient. This gets back to the issue of, and we don't want to specify a rotation point, right? So which is the tempting thing to do. But we know that that's not works. And so the answer is we have to learn this on a location by basis. So this is in some sense proof that, and the next one where the logo bends, in this case, you imagine the logo is straight, and then 3 seconds later bends, and then 3 seconds later unbends. You just sort of animated logos here. These just illustrate, again, this has to be done on a location by location basis. You can't do this like the entire child object is rotating or the entire child object is moving. We made that mistake with compositional objects. We then figured out how to do it. The same thing happens here. It has to be done on a location basis, and the system can interpolate between points, so we don't have to learn every single point. Right? So these are all very similar to what we seen before. I thought of another example, this was a weird one, and it kind of fooled me for a bit. Imagine I had a magic logo, and any place that magic logo appeared, it would move. So I would place the logo on the front of my refrigerator, and it would go up and down, up and down. And if I placed it on my laptop, it would go up and down, up and down. And I said to myself, well, that would imply that the model of the logo, the model of the behavior, excuse me, is not on the parent object. It seems like it would then be part of the logo itself. It's the logo that moves up and down. And no matter where I put it, it would go up and down. So I said, well, that seems odd. It's a counterexample. And I concluded in the end that it's not really any different. It just expanded my idea of what an object model is, a morphology model. And so I've shown a little dotted line here. And I think the way the brain would handle this is that it has a reference frame for the logo. And it has a bunch of features in that reference frame. And, or you could argue it's one feature if it's the whole logo. I don't know, but it doesn't matter. And all the features are moving. The behavior of that larger reference frame, the dotted line, is essentially that all the features in that reference frame are changing. In essence, there is still a parent object. It's just the parent object has no, it is just a concept. It's like there's a reference frame in which all the elements in that object move up and down, up and down. They have two positions they can exist in. And I know that sounds a little, you might think like a cheat, but I don't think it is. I think mentally that's how you end up visualizing it.
Oh, but couldn't you, I mean, that could definitely be happening in the lower level, but couldn't you just have a third level in the hierarchy, and basically the Numenta logo is a child on this little dotted square, which is kind of like, maybe it's like a magnet or something that you can put on different places. So basically
that's what I do. That's what I do. That's what I'm suggesting. I'm suggesting
yeah, but you wouldn't have to move the individual features in the logo. You've already learned the logo. You can just move.
I guess what I'm saying is there's an object. Well, moving features is what behaviors are, right? It's just moving reference frames in a parent object. Maybe
you're more saying, Jeff, that it's just like an invisible parent object, kind of like it's just like an anchor point.
It's an extra object that has no, that it's like Vivian said, it's like 3 levels. You'd have I'd have the cup, then there's this object which is represented by a child object, which is represented by the dashed lines, and that child object has behaviors which moves the features of the mental logo up and down, up and down.
Okay,
right. So maybe I didn't phrase it right, but the point of this is, at first I puzzled about, I really spent a lot of time trying to figure out, can I be absolutely certain that the behaviors always exist in a child-parent relationship? That is, I wouldn't have an object where the behavior applied to itself. And I wanted to always say, oh, there's always a parent-child relationship. This seemed at first like a counterexample, but I think mentally what's going on is what we just said. is that you've created a new object which is basically has no other instantiation other than a behavior where the child components go up and down. One way to think about this, imagine that rectangle was actually visible. Maybe it was like a sticker, right? And this was like a little badge. Imagine it was like a magnet, imagine it was like a magnet that goes on your refrigerator. And this magnet had a little unique icon on it. So I knew that this is this special magnet. Then anything I put in on that magnet would move up and down. So it would be like, oh, so if I saw that little magnet and then I stuck a Memento logo on it, I would expect it to go up and down. It'd be like, it's behavior of the magnet, not of the logo.
Yeah, I feel like this is a really interesting example because it kind of gets at like object physics, which is like something we've often puzzled about. But it's kind of like you can imagine gravity is a behavior like this, where it's kind of you just like put an object in that behavior basically, and it starts behaving according to gravity.
Right. That's interesting. Interesting sort of modeling physics as a behavioral, essentially a model of. It's like the refrigerator magnet, right? It's
right. And it fits because like we can imagine an object that isn't subject to physics, or we can play a video game where there's unusual physics or something like that, and so it's nice that we can apply it arbitrarily.
Right. It's a good point. It's a good point, Niels. I just want to remind you what I said in the beginning. What I'm presenting is a subset of the ultimate problems we have to have, and I'm just trying to argue that this subset is valid, and so then we would build upon it. And so that is an example of building upon it, thinking about physics and how they would apply.
Yeah, I think that would be a nice way to solve physics too, because I think that's something you also shared, Niels, that in the brain there isn't like a physics engine area or something, a specific area where physics are represented. It's more like everywhere. So that would fit with kind of behavior models of like how objects fall and stuff like that. Which just
they could fall differently in different environments, right? I mean,
yeah, and the weight of the object changes it.
Right. The Kitty Science Museum, they have a big air tube with this air going up in it, so you can put things in it and they can go up and down, up and down. Well, physics doesn't apply, but once you know that air tube, you don't expect physics to apply. It's like you very quickly learn that things can go up and down; they don't just go down. Yeah, okay, that's interesting. I don't have a picture of this, but I'll talk about it. I also thought about things like objects moving through space, like a bird flying. Or like for American baseball, like a ball that's hit in a ballpark and it leaves the batter box and it goes in an arc. And I'll just share some of the thoughts I had about that. I said, well, if a ball moves in an arc like that to the ballpark, that's not a behavior of the ball. It's actually a behavior of the ballpark. It's that. In ballparks, I expect balls to start at one point and move through the air in different trajectories. And I have a sense of where they'll end up, and I've seen lots of examples of this. And so they might bounce on the ground, or they various things. But there's behaviors that a ball could exist in the ballpark, but it's not a behavior of the ball itself. It's a behavior of the environment called the ballpark or something like that. Obviously I could substitute a different item that would perform the same, basically physics moving through space. And then I thought about a bird, and like, okay, well, a bird can move across your scene, and it's flapping its wings. Well, clearly the bird flapping its wings is a model of the bird, and I don't have to see the bird moving to see that. I could have a video of a bird. I'm just seeing it flapping its wings, and I can recognize that behavior. Like the banana walking, even though the banana's not moving. But I can also imagine, I said, well, what would it be if if the bird just flies across my scene? I'm getting a little bit off topic here, so I hope you don't mind. And I said, well, if there was no background information, it'd be very difficult to say much about the bird. But if the bird was in my living room, flying around the living room, then I could learn the behavior of the bird flying around the living room. Like the bird would go to this corner, then that corner, this corner, then that corner, bang against the window, whatever. So again, I was thinking about examples where like this ball or the bird the ball does not have any behaviors on its own that I can think of, but it can move as part of a behavior of the ballpark, in the physics associated with that. And the bird does have behaviors, but its movement through space is not part of its behavior. That's part of the spaces of behavior, you know. Anyway, just a little aside, all that was consistent. Now, we unfortunately, we started, I don't know if it's unfortunate, but we started with this example of the stapler. And that really was confusing for quite a bit. So we've already talked about the solution. I just wanted to bring it up again. In this case, the child and the parent object are the actual same object. So the two learning modules would be observing the same object. And when it starts to move, if we're going to make predictions about it, then we have to maintain the model in the child object. We can't. And so we basically decided that the way this is going to happen is that somehow the child object will be somehow masked. So it's really only attending to part of the stapler, the part that's moving. And then once you've done that, everything else works. So.
And then over time, that could be used to segment the stapler into top and bottom as like separate child objects.
It could be doing that. You know, Viv and I talked about, related to that, Viv and I talked about this issue sort of related to keyframes. And so, like, you know, do we remember all the positions of the stapler? And here's how I ended up on this. And that would be true of all these other examples, right? Do we remember all the in-between positions of the logo changing and so on? I just imagine the following. A learning module says, okay, I'm always trying to learn the morphology of an object. So I'm always attending to things, and I'm trying to make connections between the features and the locations on the object. If those features are changing or moving, I really don't have time to learn the morphology. It just goes by. I don't really have time to do it. But if the thing stops, well, then I can learn the morphology. I can continue on. So look at the example in the upper left-hand corner, the dimensional in the two positions on the cup. There's no preferred position, and I drew this diagram specifically to make it look like there's no preferred position. There isn't like, oh, the logo is supposed to be in the center and then it moves up and down. No. And so, you know, what I think the learning module would do, the parent learning module would do, it would learn the behavior of the logo of an item moving up and down, in this case, the logo. But if it stopped for 3 seconds at the top and stopped for 3 seconds at the bottom, it would learn two different morphology models of that object. It's not like there's a preference. It's not like, oh, the logo is always on the bottom and then it moves up and down. And if it stopped in between, I would probably learn that one too. So it's fluid. The way I'm proposing it, and this is true for all these things. If something is moving, you don't really have a chance to learn the morphology object. But if it stops, then you can start to learn the morphology object and you might call it as a keyframe, but it's not acting as a keyframe. And remember, I believe that this is very efficient in the brain to learn these in-between positions. So it's not like a waste of a huge amount of resources. It's very quick, but it doesn't have to be learned. That is, I can still predict where the logo will be in the middle if it stopped, but I don't have to learn it. And so it'll always be trying to learn the different morphologies of the behaviors if it has a chance. If things stop for a while, it'll say, okay, I'll try to learn this. So in all these examples I gave, I imagine them stopping every 3 seconds, and therefore I would learn all these as valid morphologies of the cup. And that would be true of the stapler as well.
Yeah, I think I hadn't thought about it that way until you mentioned it in the Slack thread. And I think that's a really nice way of thinking of it, because it's basically just taking our initial premise and ruthlessly enforcing it. Like basically, whenever something is changing, we put it into the behavior model. Whenever some static features are observed, we learn it in the morphology model. So if the logo stops somewhere in the behavioral sequence, it will go into the morphology model again. And I guess I mean, maybe the purpose of learning these different states of the stapler would then also be to efficiently recognize the stapler
Right,
once
right.
it's open. Like if you just see the stapler in its open position on the desk, it
Yeah,
would be much easier to recognize if you have actually like stored that in the morphology model, because otherwise you would have to like mentally simulate that behavioral sequence and
right.
see if that matches with your stapler model.
Also, if you take the two upper and lower the mental logos, if I would just say, oh, imagine that, and you had that cup, and then the logo went up and down every 3 seconds. It went up 3 seconds and then down after 3 seconds. If I just said, imagine that cup, you might you would imagine one of those two and maybe alternate between them, but you wouldn't imagine it in the middle. It's like, because that's not a point where it stops, right? If I just said, I'll take the cup out of the counter, either it could be moving or it could be at the top or it could be bottom. I wouldn't expect to see it in the middle, right? Because it never stops in the middle. So it sort of, it helps you infer, but it also, that's just an observation that you wouldn't know which one to predict. Then I asked myself, what if the logo went up and immediately came back down? It never stopped at the top, right? So it just went up and down. And so then there would be like, okay, the logo is supposed to be at the bottom and the behavior moves it around, but it comes back to where it's supposed to be. So I just went through all these mental things to make sure it would work, and I think they all do. I think I have one more thing on this page in here. Oops, was that it? No, I think that's it. So that's all I was going to present today. And if Vivian wants to take a stab at explaining what it is I got wrong, the parts that she was trying to explain.
No, I mean, that's, yeah, basically exactly what I was thinking too. So that's perfect.
But you did say there's the problem of transferring location. I still don't understand what that problem is.
Oh, the thing that got me thinking about it initially was the feed-forward version of how the behavior model is learned in the parent object in the first place. So how do we learn the changes in location? And the answer I came up with, and I think that you agree with maybe, is that basically it also just gets the sensory input and like it basically just learns location changes from the sensory input it gets.
Well, can I counter that? 'Cause I wouldn't use those words. If I were to guess what's going on, I would say we never learn the behavioral model doesn't learn anything about locate. It's basically learning movements. It's saying it's basically learning movements occur here at this time. So it's an
that's what I
observation.
meant.
It's an observation in the parent. It doesn't come from the child.
Well, yeah,
Maybe
basically
Vivian, if you have a diagram from one of the ones you showed last time that could help.
Yeah, let me see if I can pull one up real quick. Let's see. I'm not sure if I have the perfect one right now, but yeah, so basically this is where I started off with the one that what you just walked through, but in a much more complex diagram where
It's got a lot more
Yeah.
stuff going on here.
well, I tried to kind of build it from everything we had before, but yeah, it was a lot more confusing. But basically, this red arrow is the arrow that you had shown in green now, that like similar to how the sensor movement can move you through the reference frame, this stored movement in the object's behavior can move you through the reference frame here. So that all matches, I think. And then the second part I was thinking through was, how does this kind of local movement that we're sending down here get learned in the first place, and how does it arrive here in this column? So there are kind of two options. One is we detect that local movement in the sensor patch and then store it there. So these kind of arrows that are moving here. The second option that we could discuss maybe is that the lower region could output the location of the child object relative to the parent. And then if no, it outputs the location of the child object relative to the body. And if the location of the child object relative to the body changes, that change is encoded in here and
So
arises.
if the former solution solves the problem, it's much simpler.
Well, yeah, it's much simpler, but it relies on direct sensory input to that column. If we would also output the location of the child object relative to the body, so in a common reference frame, independent of the child object, then also higher order columns that don't get direct sensory input can learn that.
And I guess, don't we kind of need the latter for some types of behavior, like the ID change as well and things like that? Like, it seems like maybe the more general thing is that we
Yeah.
detect a change in the output of the previous column, like
Oh,
the
I
Union
see.
Jack going back and forth to the logo.
You know, the funny thing about the Union Jack is it's not clear that it's a behavior that can be generalized. You know, maybe remember I went from the logo to the flag. Maybe if I put you know, a Greek flag there, it would say, oh, I expect the Greek flag to change back and forth to the logo. But in general, it's not like the other ones. The other ones, you know, I could essentially like take a stapler that doesn't look like the stapler I learned on. It's very, very different. If I apply the behavior to it, it'll predict the position. It'll correctly predict whatever happens to the as it moves. I don't know how that would work on the ID change.
Well, yeah, so for ID change and orientation change, I basically assumed we get that information from the lower level column. So we have the detected ID from down here that goes.
But can I stop for a second? Why does the orientation change have to come from the child column? Can't that just be, imagine if I got it from the sensor. Isn't it sufficient to get it from the sensor?
I guess because I thought it's the relative orientation of the child to the parent and not just some low-level sensory orientation, so that we can, yeah, make a direct prediction about the relative orientation of the child. Same as we send the relative. So basically, I was thinking we're already sending the relative orientation of the child to the parent up here. So that already exists. And then we're just basically saying, is it static or is it changing? And if it's static, it goes into the parent's morphology model. If it's changing, it goes into the parent's behavior model.
Yeah, the way I thought about it is just take vision, and the retina provides, you know, going back to the example I've used of someone playing a video game and you're watching them. Well, the retina provides all the information you need to know about how the player is moving. And that includes changes of orientation, forward, backward, left, right, up and down, but also changes of orientation. And so that information is available, it must be coming from the retina. And so I just said, great, all that information can be picked up from the sensor. I don't need to rely on any other connections between the parent and the child object. And so that's simple. So I'm not sure that's right. I mean, maybe there's some things that you that can't be done that way. So the counter arguments are, oh, well, what about something which I'm not getting direct sensory input from? That's one counter argument. And the other counter argument might be something related to changing IDs, which I don't understand yet. So,
well, with changing IDs, I kind of agree with you that like this is not so generalizable. Yeah, I don't think we can just generalize which ID changes to what. So it's kind of like a fixed change that we'd have to store. But I guess for changing IDs, I was just, again, doing the same mechanism that we already have. We're sending the ID up to column 2 and learning that on a location by location basis. And if the ID stays the same, it gets stored in the morphology model. If it changes, it gets stored in the behavior model.
all right, I'm beginning to understand what you're saying there. In fact, what I would argue is that it's always being stored in the morphology model, even if it's the even if it's not changing. So like if the stapler, if the logo is not changing, or the staple top's not changing, there's no harm in still saying I'm looking at the logo. You know, it's the connections are there. You could learn them, but if the ID changes, then it would say, oh, now I have a new idea at this location. So I'm agreeing with you. I think the change of ID would involve the layer 3 to layer 4 connection because it's changed. But it's not a special case. It's just the layer 3 to layer 4 connections are always trying to learn connections, and if it changes, we'll have to learn some new ones. But if it's not changing, there's nothing to learn.
Yeah, and it's like you said, most of the time it would be laid down in the morphology model, like when it changed from one flag to the other, it will, most of the time there's no change happening, so we're actually learning the flag or learning the idea of the flag on the cup. But then when it changes, they're basically like that way we can know like the timing of when in a temporal sequence does the child ID change.
Yeah, it's a little bit like, imagine again the logo that's moving up and down on the cup. What if it didn't move up and down? What if it just appeared at the top and then appeared at the bottom? There was no movement in between. But we do know if the logos are close enough together, you'll perceive movement. But if you separate them apart enough, you won't perceive that it's moving. You'll just perceive that it disappeared one place and appeared someplace else. That, in some sense, very much like a changing ID, like the flag. It's like, oh, I had a child object here, and now it's gone. Oh, by the way, there was no child object up here, and now it's here. And I
Or the child object was the mug, and it's changed to.
Well, we'll say that, oh, that confused me. The mug. So I was thinking the child object's the logo.
No, but as in when it's just a mug, both the child and the parent are the mug. So there's still a change in object ID.
Right. It just changed. Right. Exactly. Right. That's up ahead of me there. Right.
Yeah, that's an interesting point because maybe that's why we like with a lot of UIs and stuff, you usually kind of simulate some movement because maybe it's easier to do this kind of movement change instead of actually having to lay down and like actually having to learn a change in object ID at a location.
Right. The brain wants to detect movement. That's why when you show two objects and you turn off one, you turn on the other, you often will perceive it as moving. You'll say, yes, it moved. I saw it moving, and it didn't move. Your brain wants to believe it's moving. But if you separate them enough, it says, oh, didn't move. This reappeared. You could also mess it up by saying, let's say the bottom logo turned off, and then half a second later, the upper logo turned on. Or maybe they were overlapping. The bottom logo's on, and for half a second, the upper logo's there, and then the bottom, so you can mess up the whole concept of movement. I guess it's really that changing. It's really like, oh yeah, you have a model, and at any point in time, a new child object can appear, and another one can disappear, but they're not moving physically.
Yeah, it could be maybe a weak argument for communicating the child object location relative to the body, because that way you don't actually have to detect optic flow in the sensor, but you would just detect a change in the location relative to the body, which doesn't have to be a continuous change. It would just be a change.
Yeah.
Yeah, it kind of feels like it doesn't need to be either or like that they would both be useful.
Maybe. I went down a real rabbit hole, Alice in Wonderland type thing, when I started thinking about, okay, do we have to incorporate both egocentric reference frames and allocentric reference frames? Like the what and the where pathways in the brain. Because when it actually comes to manipulating things, well, you need to know where they are. And so I started trying to I just got so overwhelmed with that. And then I came back and said, well, I can understand. The problem I'm trying to solve is predicting what an object's going to look like after if it's executed some behavior. And that does not require knowing where it is in the world. It's all allocentric. It's all like, just this object, I don't care where it is. It doesn't matter. It's just, I'm attending to it. And so I think when you start introducing things like body-centric, it scares me.
But I think it's actually
or maybe shared coordinate system is maybe the better term. Because at any given point or any given part of the cortex, it might be generally using allocentric or it might generally using body-centric, but it doesn't really matter.
I guess the way I would picture this, I'm happy that I could maybe solve the particular sub goals I set out, without using the other reference frame, the common reference frame. And then I would prefer then to have a problem, a task that absolutely requires the use of a third-party reference frame, or common
Yeah, I
reference
mean,
frame. And
we kind
then using that to because it's going to be a difficult thing to think about.
I mean, so like I guess 2 points. One, it's very straightforward information that would be available in every cortical column because we get the sensory input. We can get, well, I guess if it depends. So let's say it this way. In Monty and how the cortical messaging protocol is defined, we communicate in a shared coordinate system. So if a sensor, like whatever sensor modules are sensing, they sense it relative to a common reference frame, like relative to the body. So every learning module has that information of where the sensor module is relative to the body. So if it would want to output where the object is, it's straightforward. Just take the location of the sensor and add where you think you are on the object, and output that. And then that would be a perfect way to stay within the cortical messaging protocol to have that object location in the body-centric reference frame. I guess the issue with the brain is if we're only communicating movement and not locations relative to the body, then like the movement information doesn't contain this. But still, the brain, to interact with the world, would need to have a representation of relative to the body. So maybe that's just in the where pathway that's happening. But I'm just saying, like, if we assume that we get that information as input to the column, it's easy to output it again.
That's a really interesting point that you already have it there in the learning modules. I made a conscious choice this time not to show the layers of the cortex and the connections, picking up on, I think, what some of you have been doing, because I think it was really the concepts that were important, and this could be a really great example where the concepts and implementing them it doesn't matter, we do them differently than the brain. Maybe the brain has what and where pathways. Maybe we don't need that here. Maybe you've already taken care of it by having learning modules have a shared reference frame. And that may be the more efficient way of doing it. So I guess that would make my life a lot happier if I never had to think about where pathways in the brain. We just thought about the problems we're trying to solve. We come up with the right solution for them in the framework, and then you implement them the most efficient way. That would be great. So maybe that's the approach I'll take from now on. Don't think about where pathways.
Yeah, well, I think just for clarity, it's always helpful to kind of come back to the idea of just like a shared coordinate system, and then it doesn't matter too much whether it's body-centric or
Well,
like egocentric or allocentric.
I don't know what's going on in the brain, whether that's happening or not. I don't know, but anyway.
But yeah, I mean, I think there's reasonable evidence that both those kind of exist in the brain. But kind of to your point, like, how important is it that both of those things exist? Is it kind of a quirk of evolution, or
Right. Again, just like Monty today doesn't really do all this exactly how brains do it. There's a lot of things we do differently. And that's fine. I think, but the principles really matter. I mean, and so, and we've laid down really good principles so far. And so we can, as long as we stick within those main principles of what's going on, the actual implementation, I think, won't matter as much.
And yes, so I guess maybe to summarize the last few minutes, it sounds like we agree that it's reasonable maybe that location information is passed up. And if we find that it's kind of helpful or necessary, that that could inform, that kind of change in location could inform like the behavior models, and it wouldn't just have to rely on direct sensory inputs.
Although I do think, I mean, sometime the thing that brains do, I think our robots are going to have to do too, which is, detecting very quickly detecting changes in the sensory periphery, and attending to them right away. Like, what's going on over there? You know, something's happening there, unanticipated. And so I don't think we can ever get rid of that. So I'm not sure how it relates to this question. I'm not sure if, you know, sending information, location information to the child, well, the child has to know it's moving. How does the child know it's moving relative to the world, you know? But somehow there has to be very quick a way of saying there's a change in the sensory environment that is not anticipated, or and therefore we need to attend to it very quickly, because it could be dangerous. I could be falling. Something could be hitting me.
Yeah, I think in a realistic, like lower sensory region scenario, the higher column will be have a much easier time to detect movement of the child object from the sensory input than the child column actually detecting the movement of the child object itself. I guess I'm thinking a bit more like that this will become more useful if we go higher up in the regions where we don't have the sensory input and we have like movement abstract space.
So I'm agreeing with that. I said that's great. I just don't think you can get rid of the sensory thing.
Yeah.
Ultimately, we'll have to have that. I mean, well, it's going to be working in very fast-moving environments, and you know, just like humans, if you get slower, then you're in danger. Problems happen. You fall, things hit you, have accidents in your car, whatever.
Nice. Yeah, this is exciting though. I think, yeah, this definitely feels like real progress. I was wondering if it would be useful to talk through the kind of example you gave. We can either use the stapler or the logo that kind of rotated on its kind of end point. Just because, yeah, I'm still struggling to kind of visualize, like, you know, the inverse movement or whatever. It's kind of clear in my head when something just moves up and down or whatever. But if it's kind of like rotating and moving at the same time, just kind of visualizing.
Right. It's worse than that.
Yeah.
You're right. I don't think it's just those two examples. I think what I didn't talk about at all is how you go from, first of all, how do you learn a behavior model? Because we know there's lots of problems with that. Even though we have a concept of what a behavioral model looks like, we don't really have a practical way of learning it quickly. And then second, how does it actually apply to do this? I mean, it was easy to say the movement command moves the sensor, right? That works great. I'm trying today's argument. I was like trying to say it must work that way. That must be what happened. But how do you go from a behavioral model to generating the correct movement commands at any moment in time is not something I talked about. And it may not be hard, but I didn't want to think about it. It was just one more complication. I was like, oh crap! Where do I begin on that problem? So I think that's what you're asking about, Neil. There's like there's a lot of pieces here we didn't really walk through the details of. That being one of them. How does the behavior model generate the correct movements at any point in time for any module?
Maybe
Vivian's gonna have the answer.
Well, I guess how I was thinking of it was that we have these local movements stored in the behavior model, which are these kind of black small arrows, which is like, local movements of the child object.
Well, let's be careful. That's the behavior model specifies at some point in time on some location on the parent.
Yeah.
The child is moving in a certain direction, velocity.
Yeah. So
at that location only.
Yeah, right. So we're at some location in that behavior reference frame, and at that location we have stored a particular movement, like a local movement. And so it wouldn't have to be that all these arrows move in the same direction necessarily. In fact, they are not moving like the same way. They are kind of rotating and moving a bit. So, but basically we had one location in here, and there we have a local movement stored. And we would take that local movement, which is the expected object movement. That's what we expect to sense as an input here, or what we have sensed when we learned it. But then we have to invert that movement. So take the opposite of it and apply it to that reference frame here to compensate for that movement in the child object's reference frame. And
Right,
it will
right.
get more complicated if there's scale, then we also have to compensate for scale. But
Well, so that's correct, but let me tell you where I was getting tripped up, and maybe there's an easy answer to this. That makes sense, but I'm looking at one location, I say, okay, the child object should be moving. But the child objects, all the locations are moving. So a lot, maybe the whole logo is moving, or the whole staple top is rotating. But I'm only sending the movement command for the one point I'm looking at right now. And so that only tells the learning module in the child object, oh, you are expecting, this is where your sensor should be. But now I move to a different point on the object, a different point on the child object and the parent object, and it hadn't gotten those movement commands, or like, how does it know where it's supposed to be? It's sort of like saying, imagine I'm looking at the stapler, and as it's moving slowly upward, I then look at the bottom of the stapler, so I'm not really looking at the top anymore. And then I go back up to look at the top of the stapler. Well, I expect it to have continued its movement, but I wasn't sending my learning module wasn't sending any movement commands to it during the time I was looking at the bottom of the stapler.
Yeah, like it kind of feels like it gets at what we talked about a bit on the retreat. Like, do we kind of like path integrate through this behavioral space? Like, do we take all the sum of all the steps, and is that displacement applied in the top-down connection?
Maybe.
Because
Or another-
at a single point in time and a
There's
single point in
another-
space,
there's another
it's not really
solution.
sufficient.
What if you just assumed you had a whole bunch of learning modules and they covered the entire parent object and child objects, and all of them are running simultaneously? Well, then all of those would be sending the correct movement commands to the at any point in time. The problem, I think, really comes about because I was thinking of a single column or single learning.
Yeah, I mean, I was kind of thinking of it working a similar way as the occlusion working. So basically, even though we have part occlusion of the object moving, the behavior model still keeps stepping through its sequence. So we'll keep sending these movement commands in here, and we're still moving in here, even if we're not getting the feature inputs right now. But it will still keep moving you through that space.
But if this is a single learning module, it's only sending the movement commands for one spot on the child. The problem is all parts of the child are moving. So
but they're kind of moving together.
Well, there's no concept of togetherness here. That would get back to like, oh, well, we know that there's somehow that this is the fallacy to say, oh, this is an object that has it's a bar or it's a line or something like that. It's almost like you have to do it on a point by point basis.
Unless I guess we argue that if there's multiple parts moving independently, those are going to be broken up into multiple child objects.
I think that would be like the temporary attention mask in the beginning, and then later on, like Neil says, if they're moving independently, they'll be represented as independent children. And if your sensor moves between different objects, maybe the individual columns don't immediately switch their representation to the different objects, but like the column that was representing the stapler top keeps moving through the stapler top space and where it would be if we move back there or something.
I'm confused. Imagine I have a single column and it's looking at a point on the stapler top. Well, if I focus on that point on the stapler top, the behavioral model will tell me, oh, as the stapler top moves through my fixation point, the stapler top you should be moving relative to the stapler top. But now I move my sensor to the other end of the stapler top. At that point, the other end of the stapler top has not been doing path integration because it hasn't been getting any movement commands because there's nobody looking at it. And so
I think that kind of mixes up the rotation and the location. So where do we have the opening stapler?
I don't think it has anything to do with whether it's location or rotation. Pick whatever you want. It's the same problem.
Well, basically, this model here makes sure that as we are at the top of the stapler and the stapler is opening, we keep predicting the features that are here at the top of the stapler.
But only if the column is looking at that. If nobody's looking at it, then nothing. If there's no learning module tending to that point, then nothing's happening in that learning. That the only thing that the learning module knows is where it's looking at. Again, if
Yeah, I guess maybe I don't know if this is helpful, but like, yeah, maybe one way to phrase this is like, okay, imagine you just come across the stapler and it's already halfway through opening. I guess maybe the first thing you would do is, because of the movement that's been observed, you would infer that you are at a point in the behavioral space. Like you're basically at one of these kinds of points with the dashed lines.
well, actually, no, I'd be careful. If it was moving, I would infer that I'm in the behavior.
That's what I mean. If it's moving, yeah.
If it was just stopped there, I'd say, oh, it's stopped. Better learn this morphology,
Yeah.
I mean,
but then I feel like you'd start learning that morphology. Yeah.
Right.
Yeah, I guess how would you'd probably be able to say something about, oh, this was halfway through the behavior. How do you do that? That might need some sort of path integration or something, but
isn't there a time signal, is the global signal that's telling you this? So even though you're like, if you know that the behavior started, the time signal is proceeding. So if you never attend to the top of the stapler while it moved away, if you're staring at the bottom, when you go to the top of the stapler now, the state of the parent column already changed because it's getting a time signal at the end of the sequence, which will trigger it to know where it should be in the sequence, which would tell the child object, you should now look way farther to see the top of the stapler.
Right, but again, I think that's part of the solution, but I don't think it's the whole solution, because again, if there's no column looking at that point, that's moving, the whole system relies on path integration. These movement commands have to be path integrated. And so if I'm not sending the movement command to some portion of the moving object, it can't path integrate.
Yeah, but I think that we aren't necessarily very good at that either. Like if you're not looking at something and you have a behavior happening and you're like somewhere you're not looking, you have to like actively attend and mentally simulate that behavior to be able to predict where it will be when you look back at it.
So
I don't think
again, I think this would all work if I said I have a whole bunch of learning modules and I'm going to attend to all the ones there, and at any point in time, they're all someone's covering every part of this object. So I'm gonna activate the learning modules that are currently over the stapler top. Then the system would work. But if you only had like one learning module and it can only look at one part of the stapler top, I don't see how the other part, when you move to the other part, you would know where to be.
yeah, it's definitely I feel like I almost need to see it simulated or something to convince myself that it works. But it but I mean, like you say, Vivian, like worst case, maybe it's just like, yeah, we can only do it if, at least in a single or few LM situation, if we're kind of mentally really thinking about it and kind of stepping through the behavior. Yeah, I feel like maybe we need a better term than path integrated when we talk about this. Like, this is maybe a bit of a side, but yeah.
If you're listening to a song and it suddenly stops for like 5 seconds, and then you want to predict what the next note should be if you hadn't turned off the volume. It's really difficult. You have to like in your head keep counting or like keep singing the song in your head or something to be able to say what it will be when you unmute it again.
Right.
Again,
I keep coming back to the idea, can you do this with a single column? Or do you need to have many columns or sampling a whole object at once? All right, hear me out if you're following this. Here's an example. Imagine I have a single column and I've moved it over the object, and I've inferred it's the stapler. And now I'm looking at a point on the top of the stapler, and it starts to move. That might be sufficient all on its own to invoke the stapler top movement behavioral model. I can now infer the behavioral model because that's the only thing that fits a movement at that location in that direction. And therefore, it must be the stapler is opening. So I've inferred the behavioral model. And now what if that column just stays on that part of the top of the stapler, it just follows along, or if it doesn't move, the point is it doesn't look at different parts of the stapler top. If it followed it along, it would say, okay, now I made this correct prediction. I'm now, the stapler top is open. My location is sensing the part of the stapler top. Could I then infer the entire object from that one observation of being like, I'm on point X on the stapler top at this angle, therefore I can infer the rest of the object. It could be voting. It could be just like.
Well, what do you mean, sorry, the last bit with infer? Because the opening kind of description of this was we had inferred the object. Do you mean
we inferred the
do you
object,
mean
but
predict where the features are? Or?
Right. Now we want to predict, now the object is moving, and we want to predict what it's going to look, what I'm going to see after it's moved. Now,
Yeah, I think that's
to make things a little bit more complicated. Perhaps I'm looking at a novel stapler, and it may not even be the same size or the same shape exactly as the original stapler, but I recognize the behavior. And I say, okay, yes. So now I'm trying to make predictions about this novel top as it moves into new positions. And I've never seen this novel top in these new positions. I've seen
I'm sorry.
Go ahead.
Well, so at least how I was thinking of it, that would be solved by the mechanism we have, because if I understand your scenario right, we're still following the stapler, like the stapler top. So that means we're integrating the movement from the behavior that's stored at that.
But only one point. Remember, only looking at one point. Like
one point, but it means
there's nobody else integrating. It's just that one point.
I know, but it means we are still in the correct location in the child object's reference frame. We're still on the correct location there. And we're also updating the orientation of it. So we are in the correct orientation. So we're rotating the incoming movement correctly. So because we are still we're still in the correct location of the child object. We still have the correct orientation of the child object. That should then allow us to make predictions about everything else again.
Right, that's what I'm saying. That would be like almost like, yeah, then I would basically path integrate. If I move the sensor at that point in time, I would path integrate over the stapler top in its new position and orientation.
Yeah, you would use the sensor movement again to move through the reference frame. Because you were in the correct location to start with, that should work again, especially if the orientation
as long as I know where I was initially.
Yeah.
Yeah, and the incoming movements would transform by the new orientation.
I think you're right. I might give up on this concern.
I don't think you have enough information to know whether the stapler is opening or whether the stapler is translating. If you're looking at a single spot and you observe a change, the stapler could just be flying off into space. You don't know if it's opening or whether somebody's pushing the entire stapler together.
But I thought we assumed we recognized the hinge behavior. If we're not recognizing the behavior, then yeah.
Well, the constraint Jeff said, right, is you're staring at one spot and it starts to move.
Yeah, okay, that's an interesting question, Tristan. I guess, so you're right. If I'm just looking at a point on the stapler and that point starts moving, I can't know yet whether the stapler is opening or the whole stapler is moving. That's your argument.
But yeah, I mean, I think in that case, I think that's one of the main assumptions we have to make predictions. We need to recognize the behavior in order to use the behavior model to make predictions about morphology. I don't think it would work if we don't recognize the behavior. Like, I don't think I would be able to make any predictions if I was just looking through the straw and I don't know what behavior I'm observing.
Right. I think again, this might be an example where you actually might need to have multiple columns.
Yeah,
know,
but you would need them to recognize the behavior, not necessarily to
well,
That might be one where, again, it helps if you're passing the location or the change of location of the child object, because that's going to be consistent across the learning modules, or more consistent, whereas each parent LM, if it's just looking at the sensory patch it's seeing, it's getting very different kind of movement information coming in.
there's almost an assumption. I didn't follow that, Nils. I'm sorry.
Okay, that's right.
I don't know if you want to make it again, but
You go ahead. I can mention it
okay.
again.
There's this idea that the retina can detect motion, right? And if it detects motion everywhere, consistent, then it says, oh, the eye is moving. Right? The world is not spinning. The eye is moving. And but if it detects motion locally, then you assume that the object's moving relative to the world. And we've kind of and the child object moving relative to the parent object is just a sort of a special case of that, right? It's like, so we've had sort of an assumption in the background all along that we can tell the difference between an object moving versus the world moving, or the object moving versus the eye moving, and now we have to extend that same idea to a parent object. And so in some sense, there's no way in the world you can determine if the whole staple is moving or the top is moving if you're only looking at one point of the stapler top, right? It's this fact, as you point out. But we might be able to say that we have additional information that tells us whether the whole thing is moving or just part of it's moving. So I don't know the answer to that question yet, but there must be a solution to it. It doesn't bother me too much.
Yeah, and I guess what I was just trying to say was, like, going back to the kind of shared representation of the location of the object, that's also just maybe useful to vote on in terms of both recognizing behaviors, but also like segmenting the object. Like maybe something about that all these LMs are kind of saying, yes, the object is at this location, or yes, this object is kind of moving in a particular direction. That's both much more efficient if you're kind of trying to recognize how that's moving and then communicate that up to the next level. But yeah, maybe it's also helpful for the segmentation thing, because it's like, how does one LM know how to segment the object, like the top of the stapler, without some sort of information about what the other LMs are seeing?
So can I try to summarize something? It helps me to do this for me. I was worried about the fact that we would have to have multiple sensor modules, multiple learning modules observing all parts of the moving child so they all get updated by the behavioral model. And I think I've been convinced that that's not necessary. All we have to do is we can track one location using the behavioral model, but the child object is known, and now we know where we are on the child object. We know where the orientation on the child object. So if I move, I use the standard path integration to make predictions, because I have a model of the child object. This doesn't work if you don't have a model of the child object, but if you do, then the standard path integration will take you to the right place. So it's a combination of as things are moving, wherever I am, I have to path integrate using the movement from the behavior model. But if I move across the child object, I have to path integrate using the movement of the sensor. And so you have to do both these things at the same time. And as long as you do that, when the musical chair stops, meaning the child object stops moving, you will be able to path integrate the normal way and know what everything looks like. So that problem is now, I think, in my mind, sufficiently solved. I didn't think about that answer, so now that's a good. And the second thing is I'm still struggling with how we learn the behavioral model, with a single, without having lots of columns, and I haven't thought about that recently. So I still think we have to address the issue of how do we learn models efficiently using multiple columns. You know,
Maybe
even
someone
just learning
should come up with like a battery of behaviors, and then everyone has to try and learn them through looking through a straw, and then we can see if anyone actually can learn them or if it's
Yeah.
impossible.
I also think it's almost certain that even if we're just learning morphology models, we don't sense every location. It just feels like there's some sort of sharing that's going on. You already know that if you use the straw, it takes a hell of a lot longer, right? So learning seems to be doing some kind of shared learning, just like we do voting for inference. Somehow we have to be doing shared learning. So it just feels like that. So then a variation of that is the inference and learning of behaviors. So even learning morphology models seems to have to require shared learning, and maybe that we have to have shared learning for behavioral models too. It just feels like that. So maybe I'm wrong, but that would
Could be
the-
something with kind of a hierarchy could come into place too. It doesn't necessarily have to be shared laterally. It could be kind of
Right.
top-down sharing of general
Right.
models.
Every time I start thinking about that, my head spins and I get it just goes crazy. Yeah, I made this point before. It seems like when we learn a model initially, we don't learn in the lower regions. We learn in the higher regions, right? We don't learn a vision model. We learn a model like apply to vision and hearing, vision and touch, and it probably uses the hippocampus or upper regions of the cortex. And so somehow this idea that you learn sort of the upper level model then quickly and then you push it down, it's like really confusing.
Yeah.
It won't be
That's-
confusing in the end. It'll be very simple.
As we're coming towards the end of the meeting, I guess
Yeah.
just to share, I think we're making some good progress on the problems, especially now. So the last time I showed the slide, I had these gray check marks here because I didn't have any idea how location changes would be incorporated into making predictions and applying behaviors to different objects. And now I feel like we have a pretty good idea about it. So I would probably still leave those gray because we still want to kind of play through the mechanism a bit more in our head to make sure it actually works in all scenarios, but definitely a lot closer. I have one other new open question that I didn't bring up today yet related to the keyframes, but maybe something for another topic. And then also the sharing information and voting mechanism, I guess is a bigger one to talk through more.
Yeah.
But I
At
feel
some
like we're
point,
making good
at
progress.
some point we have to even
yeah.
broader, go back to the idea of, interacting with objects to create the desired states in the world, right?
Well, yeah, I think I proposed the solution to that a couple of weeks ago, that,
Did
well,
you? I
interactions
forgot.
of objects are basically just object behaviors applied to scenes. So basically the two objects or multiple objects that are interacting are just two features on a parent object, and
Right.
those moving. So it's a behavior of how two child
But
objects.
how do we make those things happen, right? How do we, how do I flip
You
the
mean
switch?
how actions come
Ye-
into this?
Yeah,
or kind of like learning causal relations, I guess, like that.
Yeah.
It's the
Yeah,
fact
I
you
guess.
pressed a switch that turned the
Like
light on, and it
today's
wasn't just
discussion
like,
was behaviors that had nothing to do with my interaction with them. They just did.
Well, yeah, I mean, actions I'm kind of taking out of this entire topic right now because I feel like
Oh, I was
that's
just saying
a
we have
whole
to do
new.
it some. I said we
Yeah,
have to do it sometime. That's all I'm
definitely,
saying.
definitely. I mean, if we already solve all of this in the next 2 weeks or 3 weeks, then we'll have a new topic for the brainstorming week.
Right. Okay, so we have you were saying we had the big question about how we do learning, shared learning. Is it hierarchical, multi-column voting, things like that? What was the other topic you said?
I didn't ask the question, but it's basically with keyframes. So if we are laying down different points in the morphology model for the different states of the object, we need some way to condition the morphology model, what to predict at what point in time, because otherwise, like, we would make predictions about the open stapler and the closed stapler at the same time. Like, we need some way to say, now I want to predict the points.
Well, I think what you need to do is like I gave the example of the logo is the top and logo is the bottom, and there's no preferred position for it, right? So somehow you have to have a morphology model that has multiple possible learned states. And
Yeah.
You wouldn't, unless one happened 99% of the time, and the other one didn't happen. If they happen equally, you somehow have to be able to infer any one of those states. And
yeah, basically a way to tell it when to predict which state. Like if I've seen the stapler open, now I want to, well, there we saw the behavior. Well, maybe it's just inference, like same as we infer rotation, we would have to try different states.
But
But
at the moment, our morphology model doesn't have the concept of different morphologies at different points in time.
yeah, so now we would
So
have
we kind of,
add
we talked about having different
dimension.
states. Yeah.
We would have to add a state dimension to our morphology models where we try to infer which.
Well, here's the possible, I know you want to end, but we do have a behavioral model, and the morphology would be associated with one point in the behavior model, and a different morphology would be associated with a different point in the behavioral model. And so this goes back to the very, very beginning, which I talked about this. I talked about states of objects. The states would in some sense be the point in time in the morphology model. And so you would be inferring not just the morphology, but also the state of the point in the behavior model. It's
yeah,
like
so we can
dimension.
we can learn like an associative connection between points in the sequence in the behavior model to states in the morphology model.
Right. It just seems
Yeah,
like,
as long as we don't try and learn tons of keyframes, I don't think it's an issue. And
well, right. And the keyframe issue is, again, I think it's less of a problem in brains because of the way they learn, but it's not required.
And it wouldn't be a lot of associations. It's like the state is like a global variable. So it would just be like point in the sequence to state in morphology model. It would be like a one-to-one connection. It wouldn't be like every feature on the model would need to be associated.
Right. So it's basically when you're inferring an object, you're looking at features, their orientation, their IDs, whatever. And you also have to, just like you're inferring the orientation, inferring the location, you have to infer the point in the behavioral state. And it's easy to say, but if you could do that, then it would work.
Well, okay, so we can check off that question too then.
Well, how are you going to do that?
It's just the same way we're doing rotation and scale.
I actually don't deeply understand the way you're doing it in Monty today, but I'm happy with it. So great, add it to your list.
Nice.
For behavior. Okay, well, maybe I'll think, personally, maybe I'll think about the shared learning problem.